Hello everyone, welcome to topic 3.12, the photoelectric effect. In this, you should be able to explain the properties of an absorbed or emitted photon in relationship to an electronic transition in an atom or molecule. There are a few equations that will be discussed in this section, and they are listed in the equations section. So, the photoelectric effect. When light shines on the surface of a metal, electrons can be ejected from the surface. This is known as the photoelectric effect. The photo prefix just describes that the electrons are ejected using light. So you fire light at it, and it kicks off some electrons. The photoelectric effect is based on light behaving both like a wave and a particle, as predicted by Albert Einstein. Light is composed of photons, with energy equal to h nu, which is the little v character. But you can say hv in class and we'll understand what you're talking about. But please note that this is not velocity. This is frequency that we're talking about, and they have very different units. So energy is equal to h nu. The image below shows the light as red wavy lines striking the surface of the metal, which is the rectangle, and causing electrons to be ejected from the surface. By measuring the amount of energy needed to remove these electrons here, we can deduce how tightly the electrons are being held in the atom. This is known as binding energy. So we can fire light energy and see how much energy, by changing this, how much energy is needed to kick off these electrons, so determining the binding energy. Greater energy values indicate that electrons are either closer to the nucleus or that the nucleus has a higher charge, because they're based off of Coulomb's law. Closer has higher attractive force, and higher charge in the nucleus has higher attractive force. Okay, so the image above shows that not all light will cause the electrons to be ejected. The red light does not have enough energy to remove electrons, being lower frequency and lower energy. The amount of energy needed to remove an electron is measured by the threshold frequency, nu naught, or the minimum amount. If a frequency is higher than the threshold frequency is used, the electrons will then be ejected with more kinetic energy. So they are ejected with a little extra energy. Okay, the amount of energy needed to eject an electron can be thought of in terms of the longest wavelength that will still eject an electron. This is called threshold wavelength. Now, remember that wavelength and frequency from first-year chemistry are inversely proportional. So any waves that are shorter than the max will have enough energy to eject electrons, and that is described in this figure here. So in summary, shorter wavelengths and higher frequency have higher energy. And so energy is proportional to frequency, but is inversely proportional to wavelength. And here's a summary of these equations, where E is equal to h nu, where E is energy, h is a constant, so it's never going to change, and it's Planck's constant, which is this number times 10 to the negative 34 joules seconds. So those units are there, so that way the rest of the math works out. And then nu is frequency with units of hertz or per second. So when we multiply these two, we end up with just joules, which is a unit for energy. We also have this one, c is equal to nu lambda, where c is the speed of light, and lambda is the wavelength in meters. It has to be in meters. So these are the units that have to go into these equations, and you may have to change them, especially the wavelength. And if you substitute in for nu, solve this equation for the v character nu, and plug it into this equation, you end up with this one, where E is equal to hc over lambda. Please make sure that you do remember that nanometers is 1 times 10 to the negative 9th meters. Okay? Because it's going to be important, because a lot of the times you'll be given nanometers and not meters. Okay, these are on the equations sheet, so you do not have to memorize them. You do need to know how to use them, though, so remember how we use them, what units are appropriate, and what you need to do to your units to make sure you can use those equations. Okay, once again, the electromagnetic spectrum, where we see increasing wavelength with decreasing energy, so they're inversely proportional. But energy is proportional or directly proportional to the frequency of the wave. So here's a little more background information. The total light energy of the light, or the photon, is equal to the kinetic energy of the ejected electron, plus the energy needed to remove the electron, or the binding energy. The energy to remove the electron is known as a work function for the substance phi. This is actually stuff that's a little extra on the background. If you took physics, this might make a little more sense. But it is not pertinent directly for the test, just knowing that these electrons are emitted and they do have kinetic energy based off of the difference in the energy put in and how much energy was required to remove it. So they do leave with a specific speed or kinetic energy. So the summary of the photoelectric effect. Energy of the photons or light must meet the minimum energy. This is given in terms of being a higher frequency than the threshold frequency, or having a shorter wavelength than the threshold wavelength. Sorry, guys. If the minimum energy is not met, the electrons will not be emitted. The rate of emission of the photons is known as the photoelectric current, which is kind of related to above. This is proportional to the intensity of the light. So how many photons at that wavelength or at that frequency are being fired at your substance. If the minimum energy is met to eject the electrons, the kinetic energy of the photoelectrons is dependent upon the energy of the light used to eject the electrons. Okay. So the idea. When a metal surface is exposed to light with increasing frequency and energy of photons, electrons first begin to be ejected from the metal when the energy of photons is 3.3 times 10 to the negative 19. Now that's when they first can start leaving or being ejected, so that means that is our binding energy. So we want to see what is the frequency of light with photon energy, 3.3 times 10 to the negative 19 joules. Okay, so we want to know what is our threshold frequency. So the equation we're going to use, if we know E and frequency is that weird V or the nu, we're going to use this equation here. So writing that out, we have E is equal to H nu, but we want to solve for nu, so divide both sides by H. So that way we get nu by itself, so nu is equal to E over H, and now we can plug in the energy of the photons and divide it by Planck's constant, which is H, and it's always going to be this value. The joules cancel out, and so we do the math, and we should get 0.50 times 10 to the 15th inverse seconds, or hertz. But this is not correct scientific notation, so we move the decimal point and adjust the exponent, and we should get 5 times 10 to the 14th hertz, or per seconds. Okay, so now we want to calculate the wavelength for that light with that energy. And we can use either one of the other two equations. We can either use C is equal to nu lambda, or E is equal to HC over lambda. I'm going to use this one just so we can practice using different equations. So calculate that wavelength, so we should be able to say that C is equal to lambda times nu. We want to solve for lambda, so we're going to divide both sides by the nu. Oops. And I wrote the wrong variable down here. And so that should be the V character. So lambda is equal to c over nu. Plug in the speed of light, which is 3 times 10 to the 8th meters per second, and then divide by your frequency from the previous question. And you get 0.6 times 10 to the negative 6. Adjusting, though, for your scientific notation, you end up with 6 times 10 to the negative 7th, which is 600 nanometers. Remembering that 1 nanometer is 1 times 10 to the negative 9 meters. So now we want to know what the color of this light is. So we're going to take this nanometer, because these are all in nanometers, and we are going to compare it to the ones over here. And so you should be able to see that that falls within the orange. And so that means that the color of the light is orange. Okay. Now for the we do. Copper 2 sulfate solutions absorb light at a wavelength of 635 nanometers. Calculate the approximate energy of 1 photon of this light. I want you to pause the video and calculate this. Remember that wavelength is a lambda, and it is asking you to find E. So figure out which equation you need to use from here, which one of these three, and solve it now. Okay, you should have gotten 3.13 times 10 to the negative 19 joules. So we know that lambda is 635 nanometers, and if we put that into meters, we should get 6.35 times 10 to the negative 7 meters. We can use the far right equation from the previous page in our notes, which is E is equal to hc over lambda. We can substitute in Planck's constant, the speed of light, which is always constant, and lambda, which is given to us as 635, but we put it in meters. Solving for it, you should end up with 3.13 times 10 to the negative 19 joules. Please pay attention to how you're putting in your exponents, because if you are off, it's probably due to how you're putting in your scientific notation numbers. Okay, complete the you-dos, check your work, and thank you for tuning in.